We perceive a universe of stars and galaxies, but this is only a fraction of the true reality. The cosmos is a dynamic tapestry woven by 15 hidden forces, and by the end of this journey, you will understand the invisible architects that dictate everything from the birth of a star to the ultimate fate of all existence. We will explore why the universe is flying apart at an accelerating rate and what mysterious scaffolding holds entire galaxies together. What one cosmic mystery do you believe holds the key to our origins? Our universe is not merely growing, it is racing outward faster with every passing moment. This accelerating expansion is driven by a mysterious repulsive force known as dark energy, an invisible pressure inherent to the fabric of space itself. Think of the cosmos not as a collection of galaxies flying apart, but as the surface of a balloon being inflated at an ever-increasing rate. Each dot on that balloon, each galaxy cluster, is carried away from its neighbors as new space relentlessly forms between them. This is not a force we can see or touch, yet its effects are undeniable. The groundbreaking observations of distant supernova by teams led by Saul Perlmutter revealed this shocking acceleration, a discovery that earned them the Nobel Prize and permanently upended our understanding of cosmic destiny. Dark energy is not a minor player, it is the dominant constituent of our reality, comprising about 68% of everything in the universe. What could it possibly be? The leading idea suggests it is a property of empty space itself, a cosmological constant that Einstein once proposed and then discarded. Alternatively, it might be a dynamic energy field that changes over time, or even a sign that our theory of gravity itself breaks down on the largest scales. Regardless of its true nature, its implications are profound. This relentless push dictates the ultimate fate of the cosmos, steering it toward a potential future called the Big Freeze. In this distant era, the acceleration would become so dominant that all galaxies beyond our local group would be swept beyond the cosmic horizon, their light forever lost to us. The universe would become a vast, dark, and ever more isolated place. How does this invisible pressure influence the fate of all cosmic structures? It is the dominant force shaping the large-scale architecture of everything we see, yet it is countered by another, equally mysterious component holding the universe together. This invisible scaffolding, the dark matter that permeates the cosmos, provides the gravitational anchor our universe desperately needs. While dark energy pushes everything apart, dark matter pulls structures together, forming a vast, unseen skeleton. Its presence was first inferred not by what astronomers could see, but by what they could not. When Vera Rubin meticulously tracked the speeds of stars orbiting within distant galaxies, she found something that defied the laws of gravity as we knew them. The stars on the outer edges of galaxies were moving just as fast as those near the center. According to Newtonian physics, these far-flung stars should have been flung off into the void, their velocity overcoming the weak gravitational pull from the galaxy's visible core. The only logical explanation was that each galaxy was embedded within a massive, invisible halo of something, a substance that provided the extra gravity needed to hold these rapidly spinning structures intact. This something is dark matter. It does not interact with light in any way, making it completely transparent, yet its gravitational influence is the dominant force shaping the cosmos on a galactic scale. Without this hidden mass, galaxies would never have formed in the first place. After the Big Bang, the universe was a nearly smooth soup of particles. Dark matter, unaffected by the intense radiation that buffeted ordinary matter, was the first to clump together under its own gravity. These clumps acted as gravitational seeds, attracting clouds of hydrogen gas that eventually ignited into the first stars and galaxies. The distribution of dark matter is not random. It forms an immense cosmic web, with dense filaments stretching across billions of light years. The glittering galaxies we observe are merely the illuminated ornaments hanging from this dark, underlying structure. So what would our universe look like without its dark scaffolding? It would be a profoundly different and likely lifeless place. Galaxies would be rare and poorly defined, stars would be scattered aimlessly, and the grand, organized structures we see today would simply not exist. This mysterious substance, making up about 27% of the cosmos, is the unseen architect of the visible world. But what is it made of? The search for its true identity leads us from the vastness of galactic clusters down to the bizarre rules of the quantum realm. The true nature of dark matter pushes us into a realm far stranger than invisible particles. To find it, we must peer into the very fabric of the void. What we perceive as empty space is a complete illusion. The vacuum of space is not a tranquil nothingness, but a seething, energetic sea. At the tiniest imaginable scales, a frantic dance of creation and annihilation is constantly underway. Virtual particles, pairs of matter and antimatter, burst into existence from nothing, borrowing energy from the universe for a fleeting moment before colliding and vanishing back into the void. This ceaseless activity is known as quantum fluctuations, and it means that there is no such thing as true emptiness. The quantum vacuum possesses a fundamental, low-level energy that permeates every cubic centimeter of the cosmos, a background hum to reality itself. The legendary physicist John Wheeler envisioned this, giving spacetime a foamy, chaotic structure at the Planck scale, a trillionth of the size of an atom. This isn't just philosophical speculation. We can observe its effects in the laboratory. The Casimir effect demonstrates this beautifully. When two perfectly smooth, uncharged metal plates are placed extremely close together in a vacuum, they are gently pushed toward each other. Why? Because the seething sea of virtual particles outside the plates exerts more pressure than the limited number of particle pairs that can flicker into existence in the narrow gap between them. The tiny push from the outside forces the plates together, a direct, measurable consequence of the energy of the void. But the influence of these quantum whispers extends far beyond a laboratory curiosity. In the first instance after the Big Bang, the entire universe was subatomic in size. Within that microscopic realm, these random quantum fluctuations were everywhere. Then, in a fraction of a second, the period of cosmic inflation stretched the universe exponentially, magnifying those tiny energy variations into the seeds of all future structure. The slightly denser patches where fluctuations had added a bit more energy began to pull in more matter through gravity. Over billions of years, those minute seeds grew into the vast cosmic web of galaxies, clusters, and superclusters we observe today. Every galaxy, every star, our very existence can be traced back to the random, seething energy of the quantum vacuum. This raises a profound and tantalizing question. Could this relentless energy of empty space, this zero-point energy, be the very source of the dark energy that is tearing the universe apart? The math suggests the energy should be astronomically, impossibly large, leading to a cosmic repulsion that would have ripped the universe to shreds before stars could even form. The fact that we exist at all means our understanding is deeply incomplete. This seething foundation is not just a curiosity, it gives rise to the fundamental fields that dictate how every single particle in the universe behaves and interacts. From the chaotic foam of the vacuum emerges the ordered reality we call home. But what process could have taken the raw potential of these fields and forged them into the stable, tangible matter that builds our world? Without the Higgs field, every fundamental particle would race through the cosmos at the speed of light. In such a universe, nothing could ever clump together to form atoms, let alone stars or people. This is the profound role of the fourth hidden force, a cosmic molasses that fills every corner of space and gives substance to reality itself. We call this the Higgs field, and its sole purpose is to impart mass. Think of it not as a physical substance, but as an invisible, all-pervasive field of interaction. As particles move through this field, they experience a kind of drag, a resistance that we interpret as their mass. The stronger this interaction, the heavier the particle becomes. A photon, the particle of light, glides through the Higgs field completely unaffected, which is why it remains massless and travels at the ultimate speed limit. In stark contrast, a heavy-top quark interacts with the field so intensely that it becomes immensely ponderous. This mechanism is what makes our material world possible. It acts as a cosmic brake, slowing particles down just enough so they can bind together into protons and neutrons, forming the stable nuclei at the heart of every atom. The celebrated discovery of the Higgs boson at the Large Hadron Collider in 2012 was not about finding just another particle. That particle was the crucial fingerprint, the definitive proof that the Higgs field itself was real. It was like finding a specific ripple on the surface of a vast, invisible ocean, confirming the ocean's existence. Without this field, the electromagnetic force would reign supreme, repelling similarly charged particles with such ferocity that no complex structures could ever emerge. The universe would be a chaotic, featureless soup of radiation and massless particles, a blinding flash without any lasting form. So the next time you feel the weight of an object in your hand, you are feeling the direct influence of this universal field, a gentle resistance that is the very reason anything has substance at all. This incredible mechanism for mass, however, is not a standalone rule. It is just one magnificent consequence of the deeper, more fundamental symmetries that write the laws for our entire universe. This sudden, exponential stretch of space solved profound riddles about our universe. Why does the cosmos look so remarkably uniform in every direction we look? The answer is that all these distant regions were once intimately connected, neighbors in a tiny volume before inflation blew them apart. And what about the overall shape of the universe? Measurements show it is incredibly flat, not curved. Inflation explains this by stretching spacetime so dramatically that any initial curvature was smoothed out to near perfection. This theory, pioneered by Alan Guth, posits that a peculiar form of energy, a false vacuum state, drove this staggering expansion. It was a phase transition, like water supercooled, and suddenly flash freezing into ice, releasing a tremendous amount of latent energy in the process. This energy did not create matter, it created space itself, inflating the universe by a factor of at least 10 to the 26 in a span of time almost too brief to comprehend. Then, just as suddenly, this inflationary field decayed, dumping its immense energy into the creation of the hot, dense plasma of particles that marked the beginning of the traditional Big Bang. But its legacy was already written. As we explored earlier, the quantum foam, those tiny fluctuations in the fabric of the void, were stretched along with everything else. Inflation magnified these microscopic wrinkles into macroscopic ripples in the density of matter and energy. These minute differences in density became the gravitational seeds for everything to come. Every galaxy cluster, every vast cosmic void, owes its origin to these quantum whispers amplified by inflation's incredible power. The theory also predicts that this violent stretching of space-time should have generated powerful gravitational waves, ripples in the fabric of reality itself. These primordial waves would have left a faint, polarized imprint on the oldest light in the universe, the cosmic microwave background. Finding that signature is one of the holy grails of modern cosmology, a direct glimpse into the universe's first fleeting moments. What could have triggered such an extreme event, and what force was powerful enough to bring it to an end? The answers likely lie in the unification of the fundamental forces, a time when the cosmos was so energetic and dense that all of nature's interactions were one. This primordial stretch set the entire stage, establishing the smooth, flat, and perfectly prepared initial conditions upon which all the other hidden forces would build our reality. But what was the nature of that reality in its very first instant, when the universe was so unified that the very concepts of space and time begin to break down? Einstein's greatest blunder might also be his most profound legacy. He originally introduced the cosmological constant as a kind of mathematical fudge factor, a repulsive force deliberately added to his equations to keep the universe static and unchanging, which was the prevailing belief at the time. When the universe was later discovered to be expanding, he reportedly discarded the idea. Yet decades later, this very same concept was resurrected to explain the shocking acceleration of cosmic expansion. The cosmological constant is now a leading candidate for dark energy, representing a steady, unchangeable energy density intrinsically woven into the vacuum of space itself. It is not a field that fluctuates or a force that weakens, but a fundamental property of emptiness, a constant pressure that pushes the universe apart. Think of it as the baseline hum of reality, a relentless, gentle push that is always on, forever acting on the fabric of space-time. If this is the true nature of dark energy, then the fate of the cosmos is fixed. The expansion will continue to accelerate, gently but inexorably driving galaxies apart until, in a distant future trillions of years from now, all but the closest galaxies vanish beyond an unreachable horizon. The universe would become a cold, dark, and profoundly isolated place, a gradual fading known as the Big Freeze. This leads to one of the most baffling fine-tuning problems in all of science. The observed value of the cosmological constant is positive, yet incredibly small. Theoretical predictions suggest it should be up to 120 orders of magnitude larger, a number so vast it is impossible to truly visualize. If it were just slightly stronger, the repulsive force would have torn the infant universe apart before any stars or galaxies could ever form. If it were slightly weaker or negative, gravity would have caused the cosmos to collapse back on itself long ago. The fact that we exist in a universe where this value is perfectly balanced to allow for structure and life is a mystery that haunts physicists. Is it merely a lucky, random roll of the cosmic dice, or is there a deeper reason for this perfect calibration? The alternative is that dark energy is not a constant at all, but a dynamic energy field called quintessence, which could change over time. Yet the steady pressure of the cosmological constant remains the simplest explanation that fits our current observations. This persistent background repulsion works in constant tension with the attractive pull of gravity and dark matter, a hidden battle that has been raging since the dawn of time and will ultimately dictate the final structure of everything. Deep within the heart of every atom, a battle of cosmic proportions is silently raging. Positively charged protons are packed incredibly close together in the nucleus, and the electromagnetic force, which makes like charges violently repel each other, should instantly tear them apart. Yet atomic nuclei remain stable for billions of years. What invisible glue is powerful enough to overcome this immense repulsion? The answer is the strong nuclear force, the strongest of all nature's fundamental interactions. This force is so potent that it can effortlessly bind protons together, but it possesses a crucial limitation. Its influence is confined to an astonishingly small domain, operating only over distances roughly the size of a single atomic nucleus. To understand how it works, we must descend to the level of quarks, the fundamental building blocks of protons and neutrons. The carriers of this force are particles called gluons, which act like a ceaselessly swapping glue, binding quarks together into the larger particles we call nucleons. But the strong force does not stop there. It also creates a residual binding effect that acts as a powerful nuclear cement, holding the entire nucleus together against the relentless electromagnetic push trying to blow it apart. Without this hidden force, our universe would be an utterly barren place. The only element that could exist would be hydrogen, a single proton with no need for a binding force. Every other element in the periodic table, from the carbon in our bodies to the oxygen we breathe, requires a nucleus with multiple protons held in close proximity. The strong force makes this possible. It is the very reason stars can shine. In the furious cores of stars, the strong force enables nuclear fusion, forcing hydrogen nuclei to slam together with enough energy to overcome their electromagnetic repulsion and fuse into helium, releasing the energy that lights up the cosmos and forges the elements of life. The theory that describes this force, quantum chromodynamics, reveals a universe of profound complexity. It tells us that the mass of a proton does not simply come from the sum of its 3 quarks. In fact, the quarks themselves provide only a tiny fraction of the total mass. The overwhelming majority comes from the pure, seething energy contained within the gluon fields that bind them, a stunning demonstration of Einstein's most famous equation made manifest. This is the microscale binder that enables macro-scale cosmic evolution, transforming a universe of simple hydrogen into a rich chemical tapestry capable of forming planets and life. Yet this force comes with a strange and absolute rule, a principle known as confinement. No quark has ever been observed in isolation. The strong force is so powerful that if you try to pull 2 quarks apart, the energy you put into the system simply creates new pairs of quarks, locking them forever inside composite particles. This perfect, unbreakable confinement is a direct consequence of the deep and beautiful symmetries that govern the interactions of the quantum world. Perfection is a beautiful idea, but it is a barren one. Our universe began in a state of such perfect symmetry that all the forces we know today were one and the same, a single, unified interaction. In that searing heat, particles were indistinguishable, and the laws of physics were simple and flawless. But a universe of perfect symmetry is a universe without character, without the diversity needed to build atoms, planets, or life. The cosmos as we know it was born from a series of profound imperfections, from the shattering of this primordial perfection as the universe expanded and cooled. This process is known as symmetry breaking, and it is the creative force that carved our reality from a featureless void. Think of it like water freezing into ice. The laws governing water molecules are perfectly symmetric, yet when it freezes, the molecules lock into a rigid, crystalline structure, choosing one specific orientation over all other possibilities. The underlying symmetry is still there in the laws, but the realized state of the system is not. The most pivotal of these cosmic phase transitions was Electroweak symmetry breaking. As the universe cooled to a temperature of 1,000 trillion degrees, a fundamental shift occurred. The Higgs field, which had been symmetric, settled into a new state, a process that gave mass to the W and Z bosons, the carriers of the weak nuclear force. Suddenly, the weak force became short-ranged and distinct, while the photon, remaining massless, became the carrier of the long-range electromagnetic force. This single event cleaved one unified electroweak force into the two separate forces we recognize today, creating the conditions for the complex nuclear reactions that power stars. But this was not the first symmetry to break. At even higher energies in the universe's first fleeting moments, a grand unified symmetry may have existed, combining the strong nuclear force with the electroweak force. When this symmetry broke, it could have triggered a process called baryogenesis, a slight preference that created just one extra matter particle for every 10 billion matter-antimatter pairs. This tiny 1 in 10 billion imperfection is the only reason any matter survived the violent mutual annihilation that should have left the cosmos with nothing but light. We are here only because of that primordial bias. These cosmic phase transitions were not always smooth. As the fields settled into their new, broken states, defects could have formed in the fabric of spacetime itself, like cracks forming in ice. Theorists speculate about cosmic strings, one-dimensional scars of immense density stretching across the universe, or other topological defects left over from these epoch-making events. The violent process of symmetry breaking would also have sent powerful ripples through spacetime, generating a background of primordial gravitational waves that we are only now beginning to hunt for. So the next time you marvel at the diversity of the world, remember that it all stems from a fundamental descent from perfection. The flawed, asymmetric universe that emerged from these breaks is the only one capable of hosting the rich tapestry of structures and life we see today. This delicate architecture, however, rests upon a set of numerical values so precise that their slightest alteration would render everything impossible. This delicate cosmic architecture rests upon a foundation of seemingly random numbers. The universe operates according to a set of fundamental constants, numerical values that are fixed and unchanging, yet appear to be chosen with almost impossible precision. Consider the fine structure constant, a number that dictates the strength of the electromagnetic force. It governs how tightly electrons bind to atomic nuclei. If this constant were just a few % larger, atomic nuclei would repel each other so fiercely that nuclear fusion in stars would be impossible. If it were slightly smaller, atoms could not form stable bonds to create molecules. The very chemistry of life would be stillborn. Similarly, the gravitational constant sets the strength of gravity's pull. If gravity were significantly stronger, stars would burn their nuclear fuel at a ferocious rate, collapsing into black holes long before life could evolve on any orbiting world. If it were much weaker, matter would never have clumped together to form stars and galaxies in the first place. The cosmos would be a cold, dark, and permanent haze. This remarkable balance is known as the fine-tuning of the universe. These constants are not derived from any known theory. They are simply the rules we observe. They set the stage for everything from the stability of a carbon atom to the lifespan of a galaxy. Their exact values seem like a cosmic lottery ticket that had to be won for us to be here. This apparent perfection raises one of the most profound questions in all of science. Why this particular set of numbers? Is our existence the result of an astronomically lucky coincidence in a single universe? Or does it point toward a staggering possibility, the existence of a multiverse? In this vast ensemble of universes, each with its own randomly selected set of physical constants, it is no surprise that we find ourselves in one of the rare habitable ones. This is the Anthropic Principle, a simple yet mind-bending explanation. We observe a universe compatible with our existence because we could not observe one that is not. Alternatively, there may be a deeper yet undiscovered law of physics that logically determines these values, making our universe not a lucky accident but an inevitable outcome. This fine-tuning reaches into the quantum realm as well, enabling the specific phenomena of quantum entanglement, where particles remain mysteriously connected across vast distances. The precise values of the constants allow for the stable quantum states that make such bizarre connections possible, weaving a hidden layer of correlation into the fabric of reality itself. These numbers are the ultimate rulebook, silently dictating what is possible in our cosmos. But what if these rules are not the only ones that could have been written? And what if the very fabric of reality allows for other, more exotic possibilities to exist? Two particles born from the same event can become a single, inseparable entity, even if they end up on opposite sides of the galaxy. Measure the spin of one as up, and its distant partner will instantly be down. This is quantum entanglement, a phenomenon so bizarre that Einstein dismissed it as spooky action at a distance. He was deeply troubled by the implication that information about a particle state could seem to travel faster than light, violating the local reality he held dear. Yet decades of meticulous experiments have proven entanglement is undeniably real. It reveals a universe where, at a fundamental level, separateness is an illusion. The properties of a particle are not fixed until they are measured, and that act of measurement somehow communicates across the vast emptiness, defining the state of its partner. This is not a force in the traditional sense with a particle carrier like a photon or a gluon. It is a correlation, a deep and fundamental connectedness woven into the very fabric of existence. This quantum link challenges our most basic assumptions about space and causality, suggesting that the universe is inherently non-local. The space between objects might be vast, but their quantum information can be profoundly intertwined. This strange connection is not just a theoretical curiosity. It is the operating principle behind emerging technologies like quantum computing. Where a classical computer bit can only be a 0 or a 1, an entangled quantum bit or qubit can be both at once, allowing for calculations of staggering complexity that could solve problems impossible for any machine today. The implications reach even deeper into the nature of spacetime itself. A fascinating idea called the ER equals EPR conjecture proposes a direct link between entanglement and the fabric of the cosmos. It suggests that two entangled particles are, in fact, connected by a microscopic wormhole, a bridge through the geometric structure of spacetime. This hints that the spacetime we inhabit may not be fundamental, but rather an emergent property arising from a vast, underlying network of quantum entanglement. The universe might be functioning like a cosmic hologram, where the information needed to describe a volume of space is actually encoded on its two-dimensional boundary. What we perceive as three-dimensional reality could be a projection from this entangled quantum data. So, while we cannot use this spooky connection to send messages faster than light, its existence tells us that the universe is far more deeply interconnected than we ever imagined. This invisible web of correlation might be the very glue that holds the geometry of reality together. The universe might be a magnificent illusion, a cosmic sleight of hand where the true action is happening on a distant, two-dimensional stage. This is the radical promise of the holographic principle, a concept that reimagines the very nature of reality. It proposes that all the information describing everything within a volume of space, every star, every planet, every one of us, is actually encoded on its outer boundary, like a three-dimensional image projected from a flat, two-dimensional surface. Think of the security hologram on your credit card. It displays a startlingly realistic three-dimensional object, yet all that information is stored on a thin, flat piece of plastic. The holographic principle suggests our entire universe operates on a similar, though infinitely more complex, principle. This idea did not emerge from pure philosophy, but from the deep puzzles of black hole thermodynamics. When matter falls into a black hole, it seems to vanish, taking its information with it. This violates a fundamental tenet of quantum mechanics, which states that information can never be truly destroyed. The brilliant physicist Jacob Bekenstein calculated that the maximum amount of information a black hole can contain is not proportional to its volume, but to the surface area of its event horizon. It was as if the black hole's entire interior was being described by bits of data painted onto its spherical surface. This resolved the information paradox and hinted at a profound truth. Perhaps this is not a special property of black holes, but a fundamental feature of all space. If the holographic principle is true, then the three-dimensional reality we experience, with its depth and substance, is a grand projection. The true, fundamental description of the cosmos exists on a remote, two-dimensional surface, a cosmic film projector at the edge of everything. Space-time itself, along with the force of gravity, may not be fundamental, but instead emerge from this underlying information-theoretic world, much like the temperature of a gas emerges from the frantic motion of countless molecules. This transforms our understanding of reality's building blocks. The ultimate constituents of the cosmos may not be tiny vibrating strings or point-like particles, but bits of information, ones and zeros, following a vast cosmic computation. How does this informational view reshape our concept of cosmic structure? It implies that the universe has a fundamental pixelation, a finite information density. There is a limit to how much detail can exist in any given region, just as a digital image becomes blurry when you zoom in too far. This informational foundation is not static, it is dynamic and deeply connected to the flow of time and the arrow of causality. The way information is processed and transferred on this fundamental screen might be what gives rise to our unidirectional experience of time, from past to future. We are living inside the most complex hologram imaginable, a projection whose source code is written in the language of information itself. This relentless march toward disorder is the hidden engine of time itself. We all feel time's arrow flying in one direction, from a remembered past toward an uncertain future, but we never see a shattered cup reassemble or a cooled cup of coffee spontaneously heat up. This one-way street is governed by a fundamental law of physics, the second law of thermodynamics, which states that the total disorder or entropy of a closed system always increases. The universe is the ultimate closed system, and it is relentlessly moving from a state of exquisite order toward one of ultimate chaos. Think of a brand new deck of cards, perfectly sorted by suit and number. That is a low entropy state. Shuffle it just once, and you have increased its disorder. The entire history of our cosmos is the story of that single cosmic shuffle playing out on the grandest possible scale. The universe began in an incredibly rare and special condition, a hot, dense, and remarkably smooth state right after the Big Bang. This was a state of surprisingly low entropy, a pristine deck of cards before the shuffle began. As the cosmos expanded and cooled, that order began to unravel. Gravity played a paradoxical role, acting as the great architect of complexity while simultaneously driving the increase in entropy. That smooth, early universe was ripe with potential. Tiny density fluctuations magnified by inflation allowed gravity to pull matter together into galaxies and stars. This seems like the creation of order from chaos, but crucially, the process of a gas cloud collapsing into a star releases a tremendous amount of heat and radiation out into the void. The increase in disorder from that released energy far outweighs the local order of the new star. A star is a magnificent temporary eddy in the great river of entropy, a brief, structured flame burning against the current that will ultimately carry it away. All processes that define our reality, from the nuclear fusion powering stars to the chemical reactions that fuel life, are possible only because they are fueled by this universal gradient from low to high entropy. Life itself is a spectacular example of this. Your body is a highly ordered system, constantly fighting off decay by consuming energy from the sun and increasing the disorder of your surroundings. You are a local pocket of order sustained by the greater flow of the universe toward disorder. This raises the most profound question of all. Why did the universe start in such an ordered state? The initial low entropy of the Big Bang is the ultimate source of time's arrow, and its origin remains one of the deepest mysteries. Some physicists suggest that cosmic inflation, that violent initial stretch, effectively reset the cosmic clock, smoothing everything out and setting up that perfect, low-entropy starting condition. Others wonder if our universe is just one region within a much vaster multiverse, and we simply find ourselves in a patch where the arrow of time points in the direction we experience. Could there be regions of reality where time flows backward from our perspective? The relentless expansion of space driven by dark energy seems intrinsically linked to this story. As the universe grows larger and colder, the maximum possible disorder within it increases, creating more room for entropy to grow and perhaps locking in time's irreversible direction. This irreversible flow is the hidden current that gives meaning to cause and effect, memory, and the entire narrative of cosmic history, a story that may ultimately be shaped by the geometry of the cosmos itself. This immense architecture is not a static monument, but a dynamic, living system. The cosmic web is a gravitational engine that has been running for over 13 billion years, its power drawn from the initial seeds planted by cosmic inflation. Those microscopic quantum fluctuations, stretched to macroscopic proportions, became the slight over densities where dark matter first began to gather. Picture a vast three-dimensional spiderweb, its silken threads stretching for hundreds of millions of light years, with glittering dewdrops caught at every intersection. The dewdrops are the brilliant galaxy clusters, and the nearly invisible silk is the dark matter scaffolding that drew them there. Between these filaments lie the cosmic voids, unimaginably vast deserts of near emptiness that can span hundreds of millions of light years. This is the true large-scale structure of our universe, a foam of matter and emptiness on a scale that dwarfs human comprehension. How did this web evolve into its present form? It is a constant battle between two titans, the relentless inward pull of gravity and the outward expansion of space driven by dark energy. In the early universe, gravity was the undisputed champion. It amplified those tiny density differences, pulling dark matter and gas into long, winding filaments and dense knots. Ordinary matter, though a minority, was swept along for the ride. As hydrogen and helium gas flowed into these gravitational valleys, it compressed, heated, and eventually ignited into the first stars, lighting up the dark matter skeleton like fairy lights on a barren tree. Supercomputer simulations, like the famed Millennium Run, have recreated this entire cosmic dance by inputting the known laws of physics and the initial conditions from the cosmic microwave background. These simulations show the universe evolving from a nearly smooth cloud into the intricate, web-like structure we observe today. They are time machines allowing us to watch as virtual galaxies form, collide, and merge over billions of years of simulated time. The final distribution of galaxies in these simulations is a near-perfect match to the maps we create with our most powerful telescopes. This grand structure does more than just host galaxies. It actively shapes their destiny and guides the most energetic messengers traveling through the cosmos. The gravitational field of the entire web acts as a colossal lens, bending the path of light from distant quasars and galaxies. It can distort their images into faint, shimmering arcs, or even create multiple copies of the same object in the sky. This phenomenon, gravitational lensing, allows us to map the invisible dark matter directly, tracing its distribution by observing how it warps the light from background galaxies. The cosmic web is the universe's ultimate information superhighway, but also its most complex obstacle course. The journey of a photon from a distant gamma-ray burst, one of the most violent explosions in the universe, is not a straight line. It weaves through the gravitational hills and valleys of the web, its path subtly altered by every filament and void it passes. Even the most energetic particles, cosmic rays traveling at near light speed, are deflected by these vast magnetic fields that are thought to be woven through the web's structure. The architecture of everything is written in this gravitational blueprint, a hidden force that has choreographed the rise of galaxies and now guides the very light by which we see them. Threading through the immense voids between galaxies are invisible lines of force. These cosmic magnetic fields are unimaginably vast, stretching for millions of light years, yet their strength is almost negligible, far weaker than the magnet on your refrigerator. But in the near-perfect vacuum of space, even this faint influence becomes a dominant power over the thin soup of charged particles that floats between the stars. They are the ghostly railroads of the cosmos, guiding and channeling the most energetic particles in the universe. The origin of these universal fields is a profound mystery. They must have started as incredibly faint seed fields, traces of magnetism born in the universe's chaotic infancy, perhaps from the violent plasma of the Big Bang itself or from the first supermassive black holes. Then a cosmic amplifier took over. As vast clouds of gas collapsed to form galaxies and stars, their rotation acted like a natural dynamo. Just as a simple bicycle dynamo spins a magnet to generate electricity, the spinning motion of these cosmic structures wound up and amplified those weak seed fields, weaving them into the pervasive magnetic tapestry we detect today. Without this magnetic influence, our galaxy would look profoundly different. When a giant cloud of gas begins to collapse under its own gravity to form a star, it spins faster, just like an ice skater pulling in her arms. Left unchecked, this rapid spin would fling the material apart before a star could ever ignite. Magnetic fields solve this. They act as a cosmic brake, transferring that spin energy outward and allowing the cloud to continue its inward collapse. They are the unsung midwives of star birth. Once stars are formed, these magnetic fields become cosmic particle accelerators. They grip high-energy protons and atomic nuclei, the cosmic rays that constantly bombard our planet, and funnel them across the galaxy at nearly the speed of light. These raging particles are a vital part of the galactic ecosystem, and without magnetic fields to contain them, they would simply fly off into the intergalactic void. The most dramatic enrichments of these fields come from stellar death. When a massive star explodes as a supernova, it does more than just blast newly forged elements across space. The incredible violence of the explosion sends shockwaves through the surrounding magnetic fields, twisting and strengthening them, while the spinning remnant of the dead star, a neutron star, often becomes a powerful magnet in its own right. These events seed the cosmos not only with the raw materials for planets and life, but with the very magnetic forces that will shape the next generation of stars. So the next time you look at the silent stars, remember they are embedded in a universe crisscrossed by these invisible threads, a fundamental force that guides the birth of suns and the journeys of the most energetic particles in existence. The faint echo of a primordial sound is permanently frozen into the cosmos. In its first 400,000 years, the universe was a seething, opaque plasma, a roiling soup where light was trapped, endlessly bouncing off a dense fog of protons and electrons. Within this hot fluid, gravity acted as a constant, gentle pull, trying to draw matter inward, but the intense pressure of the trapped light pushed back, creating a continuous struggle between collapse and expansion. This battle generated powerful sound waves, spherical pressure fronts that raced outward at over half the speed of light. These were the Baryon acoustic oscillations, a rhythmic pulse thrumming through the infant cosmos. Then, in a moment known as recombination, the universe cooled just enough for atoms to form. The electrons were captured by protons, creating neutral hydrogen, and the fog of plasma suddenly cleared. The light, now freed, streamed across the universe as the cosmic microwave background. But the sound waves did not simply vanish. They were frozen in place, their progress halted in mid-ripple. Each wave left behind a spherical shell, a subtle overdensity where matter had been gathered at its leading edge. Imagine a pond instantly turning to ice, capturing the circular ripples from a dropped stone at the exact moment they reached their peak. Across the entire cosmos, this happened on a single, universal scale. The diameter of that frozen shell, that preferred separation, became a cosmic standard ruler, measuring about 500 million light-years across. Today, we can still detect this ancient rhythm by mapping the positions of millions of galaxies. When astronomers measure the clustering of galaxies across the sky, they find a subtle but statistically significant excess of pairs separated by that exact distance, the 500 million light-year scale. This is the fossilized imprint of those sound waves, a ghostly pattern woven into the very distribution of matter. This standard ruler is our most powerful tool for measuring the geometry and expansion of the universe. By observing how the apparent size of this ruler changes at different cosmic distances, and thus different points in the past, we can measure the expansion history of the cosmos with incredible precision. It acts as a direct probe for the properties of dark energy, telling us whether its repulsive force has remained constant or changed over billions of years. This ancient echo, a vibration from the universe's first moments, has become one of our most reliable guides to its ultimate fate. Together, these 15 hidden forces weave a single, continuous narrative of cosmic evolution. These 15 cosmic architects do not work in isolation. Their power emerges from a breathtakingly intricate dance, a symphony where each force plays its part in perfect, if chaotic, harmony. Dark matter's relentless gravity sculpts the cosmic web, providing the invisible canvas upon which everything is painted. Yet dark energy's constant, repulsive push dictates the tempo of the entire performance, controlling how fast that canvas is stretching. The quantum vacuum provides the initial, random notes, the microscopic fluctuations that inflation amplified into the gravitational seeds for all structure. It is the Higgs field that gives those structures substance, transforming ethereal energy into stable, tangible matter that can coalesce under gravity's pull. And underpinning it all, the fundamental constants act as the unchangeable sheet music, the precise numerical rules that make this specific symphony possible. From the spooky, instantaneous connection of entangled particles to the vast, slow-motion choreography of galaxy clusters, these phenomena are deeply intertwined. The initial conditions set by cosmic inflation directly led to the frozen sound waves of the Baryon acoustic oscillations, an echo we now use to measure dark energy's strength. The breaking of perfect symmetries in the hot, early universe generated the critical 1 in 10 billion matter-antimatter imbalance, the very reason we exist at all. This synthesis reveals a cosmos that is a single, coherent, and dynamic system. The past, present, and future are woven together by these collaborating forces. So where does that leave us? We are not merely passive spectators to this grand drama. We are a product of it. The carbon in our cells was forged in stars whose birth was guided by magnetic fields and whose stability relied on the strong nuclear force. Our ability to observe and question the universe stems from a consciousness that itself may be a manifestation of this complex, self-organizing cosmos. We are the universe awakening to itself, a fleeting but profound moment in a story written by 15 hidden hands. This grand cosmic symphony, composed of 15 hidden architects, reveals a universe of breathtaking dynamism and connection. We have journeyed from the repulsive force of dark energy, accelerating the cosmos, to the binding grip of the strong nuclear force holding atoms together. We have seen how the quantum foam provides the raw material for reality and how the Higgs field gives it substance. These are not isolated phenomena. They are threads in a single, magnificent tapestry, working in concert to sculpt galaxies, dictate the relentless flow of time, and determine the ultimate fate of all existence. These mysteries are not distant abstractions for physicists alone. They are the very same forces that carved our planet from stardust, that ignited our sun, and that assembled the complex molecules that became us. Every atom in your body is a testament to a cosmic battle between gravity and pressure, a relic from a star that lived and died long before our solar system was born. The human drive to unravel these secrets pushes the very boundaries of knowledge and technology, leading us to build colossal particle colliders deep underground and launch telescopes that act as time machines, peering back toward the dawn of everything. So the next time you find yourself under a clear night sky, let your gaze drift across the starry void. Look up with a renewed sense of wonder, knowing that you are witnessing the ongoing performance of a drama written by invisible hands. What other profound secrets is the cosmos holding, waiting for a curious mind to uncover them? We would love to hear which of these hidden forces you find most fascinating. Share your thoughts in the comments below, subscribe for more journeys into the heart of space mysteries, and never, ever stop questioning the universe around you.